The coupled inductor is kind of a transformer. In this lecture, in the electric circuit, we don't need to discuss about the principle of transformer in here. It will be deal with maybe the principle of transformer. You need to know to understanding the transformer's principle. You need to know about the magnetic field, magnetic circuit. Magnetic field and magnetic circuit will be discussed in the electromagnetism in another class, and the electric energy conversion theory will be covered in other classes. So in this class we will discuss about the transformer very simply. So because this is because this is inductors, so we can rewrite here is V1. The here is the same voltage here. This is a V1 because the V1 is connected directly to the first the primary wire. So it will be L1 dt di1. And here we define L1 is a self-inductance. So ion make a in I1 make a magnetic core. Flux. So I1 generate the magnetic flux. I'm saying magnetic core here. So the flux caused by I1 is phi. It's a flux. When it's determined by the magnitude of I1 and material characteristic of core and turn number of the winding. Actually, this is not important in this stage. This is very important in the electromagnetism and the energy conversion theory, but in the electric circuit, we don't care about what is that. So anyway, the reason I explain the principle of that is you need to understanding what is self-inductance and what is mutual inductance, that's all, and coupling coefficient. So let's define the set of pi1 is a magnetic flux caused by the current I1. So it can be written here is C1, N1, and I1, the magnitude of current of the primary winding. We call this is a primary winding. This is a primary winding. And call this is a secondary winding. So here, this is I1, and here is a turn number, and here, and I don't know the material characteristic of core exactly to express the phi one, but I don't care about that. But anyway, we discuss about that is let that is a C1 here. So we know the Faraday law. So the is E is N dt d phi. That means the variation of flux, the variation of magnetic flux causes a voltage. So based on that, because the current is AC, the current and here is AC, so flux is varying according to the current. So we can say that the V1 voltage is here and that voltage here. The V1 is N1 dTd phi 1. And your phi 1 is that, so it'll be N1 dTd C1 N1 I1. So you can read it in here, C1 N1 square dTd I1. So we know that this is the relationship between current and voltage in the inductance. So based on the Faraday law, we can make a similar form of that. Is the relation between the voltage and current. So therefore, N1 can be re-expressed with C1 N1 square. So therefore, the inductance is proportional to the turn number square. So this is very important here, the characteristic in the real system. So anyway, we can assume that the L1 is C1 and N2. And the flux is common in the magnetic, in here. Flux is common in the magnetic forward. So this phenomenon happened in the secondary winding. So we can rewrite the voltage here. This is a voltage V2 and this I2. We have the same things here. In the secondary winding, we have the same phenomenon here. So secondary winding voltage V2 is N2 dTd phi 2. If all flux, generated by flux is flux 1, this is the couple here, you can define this is a flux 1, phi 1, and coupled here, we define is phi 2. If, I don't know the value of that, if let phi 2 is same with the flux, I make sure exactly phi 2 is the flux coupled in the secondary winding. So we define that as a N1 I1, and we have another things here. This is, we can define Cm. Why we does not use the C1 is, the flux generated by the primary winding here is something coupled, something go to the secondary winding in this way here. But something is not go, something is not go to the secondary winding. It is make a loop in this way here. So in this flux does not common with secondary winding. So we need to figure out. So the generated the voltage in the primary winding is phi 1. So that is that things. But the phi 1 is not coupled all phi 1 is not coupled with secondary winding. So we need to distinguish of the atoms. So to distinguishing the coupled, the flux, so we define Cm. Because N1 and I1 is the fixed values, so we define the Cm. So Cm means the characteristic of core. So if Cm equals C1, that means there are no flux leakage. Leakage means that this is, we call this is leakage. Leakage means that the sender is neutral. In Korean is neutral. But generally, Cm is smaller than C1. Why? The C1 generates the phi one, but among them, some part of flux coupled in secondary winding. So we need to distinguish the Cm. So the flux is, the flux caused by the primary winding is coupled in secondary winding, but all of that does not couple the secondary winding. So phi 1 and phi 2 is a coupled flux to the secondary winding. So we define in this way here. So we insert is N2 dTd Cm N1 I1. So there will be Cm N1 N2 dTd I1. So we make a very similar terms here, but we define this is a relationship between voltage and current. So we define, this is another name of M. Cm, Nn, N1, N2. Because this is a mutual inductance. This is inductance related to the coupled magnetic flux with secondary winding from flux caused by primary current. If all this is inductance, the mutual inductance. If there are no leakage, then the mutual inductance is the same with the self-inductance. So, but we don't need, in the circuit theory, we don't need to about the principle of the coupled inductor or transformer. We will deal with the coupled inductor kind of the inductor, but a little bit complicated compared to the simple inductor. So we define here, is very important here, very important. So we will express coupled inductor in this way, in this manner. And we make some dot here. Make it this dot here and here. And we express, this is M. M is mutual inductance. And we define the voltage here is V1T, and current direction is here I1T, and this is the direction of here I to T, and we define this is the V to T. this is a two terminal systems. Two voltages and two current. So if if there are the coupled inductor in the electric circuit, then you make a equation based on this principle I will discuss here. So at first, if rule 1 if I1T go to that, then that terminal of secondary winding is the positive voltage. Here. And rule second, same things. If I1T come out of that, then terminal of secondary winding is negative pole. We call this is a dot convention. What's the meaning of that is we could define as a dot convention. The reason is the polarity should be the polarity of primary winding and secondary winding can be different, because this is the way to winding the direction. When you make a winding in the core, according to the direction of the winding, the polarity can be different. So we need to define, if we have a transformer, then we need to know the direction of that. So to express the direction, we use the dot conventions. That convention is that this is a primary here, this is secondary here. We make a dot here. The reason is we define the current IT this way, and we make the voltage here, V2T. Then what's the meaning of that is, if the primary current increase, then means DTD I1T is positive, then define the V2T is positive at that terminal. That's that conventions. We can do that here. We will have some example here. This is coupling here. We have two terminals, therefore two voltages, two current, and this coupling inductor is looks like that. Mutual is M, and that is expressed here. So I want to gather the voltage and current relationship here. So I can define my voltage and current. I define this is a V1T, and I define this is I1T, and I define this is I2T, and the direction is going to the dot, and define this is a V2T. You can do that. You can change the directions as you want. Then the relationship between the voltage and current here looks like that. The V1T is a kind of we will define the self-inductance of that is L1, and this is L2, this self-inductance here. So because inductance, the current is go to the inductance L1, so we have L1 dTd I1T. This is simple. Why? We define that there are some inductance here, L1 inductance here, and we define the voltage in this way, V1T, and current is defined in this way, I1T. Therefore, from that, we can get a relationship between voltage and current. So V1T is L1 dTd I1T. This is the only simple relationship between the voltage and current in the inductance. But coupled inductance has one more terms. The coupled inductance has an effect each other from the first winding, the primary winding and secondary winding. Therefore, we have one more voltage here. That voltage is caused by the secondary winding current, that terms. So, but the effect caused by the I2T, the secondary winding current, the inductance is not L1, this is M. Why? M is a close coupled inductance values. So we can use M dTd I2T, I2. But here, we need to check out this direction here, this polarity here. Based on the dot convention, we define that when you go into the current in the dot, then the other side, the polarity, the dot terminal has a plus polarity. So we can say that because I2 is go into the dot, so therefore the caused voltage of the atom M dTd I2 has a polarity, has a positive values in that point. But we define I1 is that plus here, the same directions, so we can choose this is a plus. In the same way, we can express the V2T here. So V2T here, current is going into the L2 here. So the relationship between the V2 and I2 caused by L2 is a self-inductance. You can write L2 dTd I2T here. Because this is a coupled inductance, the V2 also has some effect from the primary current, the I1T. So the voltage term caused by I1T by the mutual inductance M is M dTd I2. So we can use the dot convention here because I1 is going to the dot. So this amount has a positive polarity is this term plus, but the V2 is plus at positive, so the same direction, so it's plus. So we can transfer from this coupled inductor and it's a two voltage current equations. So that is only things we need to know the coupled inductor when you did analysis the coupled inductor circuits. So we can make a similar but other cases here. We have coupled inductor here. Here, the mutual inductance is M. Itself is L1 and L2, but that is different. That here, and that here. Then I can define the variables V, L, I as we want. So at this problem, I will define the voltage here. V1T. This current is I1T. And we define this is a V2T. That is what we want. We can define the voltage as we want. We define the direction of I to T in this way here. Then we want to gather the relationship between voltage and current. Okay, the first thing is I want to get a V1T. V1T is, this is self-inductance, the primary current going into the positive direction of voltage. So we can gather N1 dTd I1 here. And because this is coupled inductor, we have the voltage caused by secondary current. This with a mutual. So there is the M mutual inductance dTd I to T. But we need to figure out the direction of the voltage caused by I to T here. I mean, I to T going into the node terminals. So therefore, this voltage term has a plus polarity at the node point here. But this point is a reverse of I1T. Therefore, we need to insert the minus sign here. In the same way, we can define the V to T here. V to T has a deep then we define the V2 direction is plus here, and the I2 current going into the plus polarity. So we have like that. We define the V2 in this way, and current is going into here because I to T go into the positive values of VL2, V2. So the V2 is L dTd I2. In the same way, we can do that. L2 dTd I to T. And because this is a coupled inductor, the caused by the I1T voltage is refracted in the secondary voltage here. The amount of that is M dTd I1T. So we need to check out the direction. The I1T go to that point. Therefore, the voltage caused by I1T has a plus polarity, this dot here. So this point is a positive, but this point is a reverse direction of here is V2. So there is a minus. So, and we can make another example. This is the same polarity form here, and here. We define, I will give another example here. In the same polarity, that, and mutual is M, this is L1, this is L2. I told you that again and again. The direction of the voltage current, you can do it as you want. So in this time, I define voltage here. This is V1. V1T, and I define this is I1T, and I define this is V2T. I define the direction is I to T is the reverse, and in this case it going into the dot, but in this time going up, come out from the dot. Then we can make a equation. And first V1T, because this is N1, but I want to go into the positive V1, so this is N1 dT I1T. And we have another term caused by secondary current, so that term is M dTd I to t. We need to know the polarity here. So I to t come out from the dot, then means out to t going into the no dot. Therefore, this voltage is positive when no dot here. But this is the reverse of V1, the positive values. So this is minus. So, and V to t here, because we define the V to t plus here, I mean this inductance, and define the V2, but the current is going out from the I to here. Therefore, the voltage inductance is L2 dTd I to t, but the direction is minus. Why? When you define that this V1 is L dTd I, then the direction of current is going into the plus direction of voltage. Then we have these relationships. But we define the I2 is a reverse, so this is minus. And we have another term, this is a M. So we have another term, M dTd I1t. We need to know the direction of here. The I1 is going into the positive dot. So this amount is a positive. This is a dot here. This is dot. So the same direction of that is a plus. So these, the coupled inductor can be represented in the relationship. And another example, in another case, we can make another case. And here, this time, this is that here, and this is that here, and we choose M, self is L1, this is L2. And I decide, in this time, I decide the voltage I1t, and I decide, this is case, I1t, and I decide this voltage is V to t, and this side current addition is I to t. Is a different. So I want to calculate, I want to get the voltage and current relationship here. So V1t has two terms. Itself L1 dTd I1t and M dTd I to t. Because the direction of I1 is this direction, is going into the positive values, so this is a plus. And because that direction is here, so current I2 is going into that. So that means the caused by voltage by I2 has a positive where the dot is a positive. So this plus dot and plus is the same direction, so this is a plus. And Vt has two terms, L2 d I to t, and M dTd I1t. So we define that the direction is when you calculate simple L, you define the voltage plus and current is in this direction here. This is a relation I2 and V2. So therefore, that is a minus. And in the case, the I1 is going to that. Therefore, the voltage caused by I1 is that is a positive, but that and plus is a reverse, so that is a minus. So based on the position of the dot, you can write the voltage and current, the equation from the coupled inductor. It's very simple, but you need to have some exercise. This mutual characteristic of the coupled inductor can be represented in the independent source. We call this as the modeling. So we can make the mutual inductance modeling. by dependent source. So we have mutual inductance in this way here. So this is that and that. The couple, mutual inductance is M. The self is L1, self is L2, and we define the voltage here, V1T, and make a deduction of current is I1T. And I define the voltage is V2T. The deduction of current is in this way, I2T. Therefore, from that, we get an equation of voltage and current. The V1T is L1 dTd I1T plus M dTd I2T, and V2T is L2 dTd I2T plus M dTd I1T. So we can make the model with a dependent source. So the model means this equation is a representative characteristic of the coupled inductors. So modeling means we represent this relationship with the other component simply. So we have terminal here. This is a V1T, has a first term here. We define the direction of current is I1 here. Then we make a L1. So this is L1. Simple inductor. And we have another voltage here. So we remodel here is dependent source like that. And this is a M dTd I2. In the same way, we make a voltage terminal V2T, and we define the current direction is I2T. Then we met inductors here, L2, and have a different the voltage source here, plus minus. This is M dTd I1. So using the dependent source, dependent voltage source, we can model the coupled inductor in this manner. But the coupled inductor is a very key, very important the element in the AC circuit. The coupled inductor is based on the Faraday law. The voltage is induced by the flux variations. So the voltage should be variations. So the AC circuit, the coupled inductor operated in only AC circuit. So we can rewrite here. If we have the relationship as voltage and current. Then we can change this term with a pager. When you say the V and V1, V2, and I1, I2 is sinusoidal, then we can rewrite here. V1 is, because L is the impedance, so J omega L1 I1 plus J omega M I2. And V2 is J omega L2 I2 plus J omega M I1. So when you solve the coupled inductor in the pager, you can change the pager as you know in the way to impedance. And you know that we already discussed is about the modeling of the inductance here. So we define the L1 is in this manner. L1 is C1 N1 square. The C1 is a characteristic of the core. And in the same way, we can rewrite here, we'll want to discuss about coupled coupling coefficient. Okay. And we have a core. We simply looks like that. And primary core is coupled like that, and secondary looks like that. And then the inductance of N1, N1 was C1 N1 square. In the same way, L2 is C2 N2 square. So from here, we can calculate an L1 and L2, C1, C2, N1 square, and N2 square. So that is N1, N2 root C1, C2 square. So to represent here is CM square C1, C2, and N1, N2. We can represent the same things. Then we can represent here. Here, and we already know that the coupling coefficient is, we define the coupling coefficient Cm is no. We define the things M is a Cm N1 and N2. We define this manner. So that will be Cm square and C1, C2, Cm. I'm sorry, it's wrong. It's not Cm square. This is M square. M square. So here we define that this is a K. It is K M2 squared. So K equals C1, C2, Cm. We define the K as a coupling coefficient. And that means we define this as C1, C2, Cm. So this is a kind of a value to show the how much the primary winding and secondary winding are coupled. So when you say the K is 1, and say K is 1. It's perfect coupled. That means no leakage. So physically, the K1 is 1, is that means all flux caused by the primary winding is coupled with secondary winding perfectly. And you can say K is 1. In other words, K is 0, that means no coupled. 100% leakage. That means there are no relationship between the the L1 and L2. Because K was 0, that means Cm is K squared C1 C2, that is 0. Therefore M is 0. The M is 0 means you say V1 was L1 dTd I1 plus M dTd I2. The V2 is L2 dTd I2 plus M dTd I1. For example, this is a coupled inductor here, V1, V2, I1, I2 case. Then here, the K is 0, means M is 0. Then means it's 0, 0. So this is a V1 is L1 dTd I1, and V2 is L2 dTd I2. That's it. That means there are no coupling here between two coils. So this is the same way, only one inductor and the other inductor. That's it, no coupled. So in the case of the K is a 1, the K is a 0. Next is about the couple values here. In this time, we need to discuss about the power. The instantaneous power were in coupled inductor. In Korean is 순시 전력. We have an example here. Is coupled inductor in this manner. The coupled inductor. This is that, and that, and this is the Vt. We define this V1t and define the direction of this I1t, and define the voltage of V2t. And direction of that is I2t here. Then what is the power? In power, PT, we have two voltage and current. So we need to calculate this power and this power. So in terms of power, it's sum of the two powers. So this is V1 T I1T plus V2T I2T. So if we have an example, we couple impedance is M here, and this is L1, this is L2. So from that we can calculate the principle of that. This will be power and the relationship between voltage and current. V1T is L1 dTd I1T plus M dTd I2T, and V2T is L2 dTd I2T plus M dTd I1T. So if insert this term, let's go here, then this term can be represented in, this is L1 dTd I1 plus M dTd I2 and I1 plus V2 here, L2 dTd I2 plus M dTd I1 and I2. So we need to calculate, that is L1 I1T dTd I2T, oh I'm sorry, it's long, it's not I2T, I1T dTd I1T, because this here and here plus M I1T dTd I2T plus that L2 I2T dTd I2T plus M I2T dTd I1T here. Then we need to think about and this term and this term. This is M I1 dTd I2T, I2 dTi I1T. So therefore we combine this is M dTd I1T and I2T plus N1, this is N1 I1T dTd I1T plus L2 I2T dTd I2T. So this is instantaneous power in coupled inductor here. Then we need to know about the energy. And next we will discuss about the energy here. There will be energy is integral minus infinity to p tau d tau here. So there will be minus infinity to t. Yeah, we add in these terms here. So L1 I1 tau dTd I1 tau plus L2 I2 tau dTd I2 tau plus M dt d I1 tau I2 tau d tau. So that will be half L1 I1 tau square minus infinity t plus half L2 I2 tau square infinity to t plus m I1 tau I2 tau minus infinity to t. So if we neglect now the minus infinity value is 0, so that will be I square plus half L2 I2 square plus m I1 I2. So this is the energy, stored energy in the coupled inductor. So from there, we can get the variation, the range of the M, the mutual inductance. M, we can calculate the range of M is mutual inductance. Because mutual inductance is a passive component, so this is a passive component. Therefore, energy should be positive. It could be the negative. What's the meaning of the negative? Negative means energy is transmitted from the device, that is a battery. So the energy stored the coupled inductor should be positive or 0. Therefore, the energy here, WT is half L1 I1 square plus half L2 I2 square plus M I1 and I2 should be positive. So to get that here, we can that can be rewritten here is L1 I1 plus minus square minus plus L1 L2 I1 I2 plus M I1 I2 will be that values. So you can rewrite here is half L1 I1 plus or minus L2 I2 square plus I1 and I2 minus plus L1 L2 plus M should be positive. But that is a positive when this is always positive. So this is always positive. So these relations, because this is should be positive values, this should be positive. And there, I1, I2 minus plus to L1, L2 should be positive. When I1 is minus plus L1, 2 I2, then this is positive. So in these conditions, the voltage should be positive. So insert that value of there is there in this manner, then the result is N1 2 I2 square N1 L2 minus N should be positive. Be positive, therefore this should be positive. Therefore N should be small and L2. So this is the maximum value of the M. So this is the same result we discussed the coupling coefficient here is the maximum value is case 1. That means in this case the case 1, so that means Cm and that value is the same things. So in this case M is a C1, 2, N1, N2. The same result of this and this result. So coupling coefficient is K, and K is should be smaller 1. Therefore, the range of K is that. When you say the K is similar, I mean K is 1 is kind of transformer. K is similar to 0, that means it's a radio circuit. Have you ever heard the wireless power transfer? So, wireless power transfer is kind of a very huge the gap transformer. The reason the coupling coefficient is high in the transformer is the core. This is core. This is called the core, and winding here the primary winding and secondary winding, and this distance is L is very small. This is transformer. This is transformer. This is a high K. And generally, if you remove increase the length of these distance between two cores like that, L increase. L is relatively high. Yeah, large. Then the K is decreased dramatically. So there are no power transfer between these Ks. This is a bad transformer. This is a bad transformer. But what is the wireless power transformer? With wireless power case, so they make a huge the gap to cores here in primary first winding and secondary winding, and they make some capacitor in this manner. It could be series or parallel. There are many topology here. So because that they make the increase K is very high. So that's the wireless power transfer. So this is, I mean, it can be understood kind of a transformer, but the gap is very huge. But they're adding some capacitor in both sides, primary and secondary windings. So you make an increase in the coupling coefficient. So they make a big coupling between two coils. So it is kind of the wireless power to transform.